Air tankers or water bombers are one of the most effective tools we have when it comes to controlling forest fires, especially those ones that are rapidly spreading or very intense. The core purpose of them is to knock the flame front down or the intensity so that crews can get up along the flank or the head of the fire and establish hose lines in and ultimately extinguish that. There are many different types of air tankers. In Ontario we have the CL415 and the Twin Otter, but we also utilize contracted belly tanked helicopters. And then of course nationally there's CL215s and 802 Fire Bosses. So each one of these air tankers performs a little differently. So with this project we're working with primarily the Canadian Forest Service, as well as some of our other academic partners like FPInnovations, the University of Toronto, and some of the other fire agencies. And in a nutshell, we're looking to build models so that we can identify the effectiveness of different air tankers in different fire situations.
It started with a simple question about what's the difference between the drops coming out of different tankers, right? And I think we started on a process to try to look at, well, what is water? What water is landing? What is that water doing to a fire? And we thought about the physics of that.
So we're using an atypical strategy for this. We have a very sophisticated infrared camera, and we're measuring the temperature differential on the field as the water comes in. So we can see things that you normally wouldn't get out of a cup test. We can measure the velocity of the water as it falls from the aircraft, the temperature of it. We can see the actual extent when it hits the field. What does that pattern look like? We can also, if all goes well, we should be able to estimate how long that water drop is effective and how the water is concentrated within the drop itself.
So one of the ways this was approached conventionally is a grid of cups is placed out in a drop area, every so many meters, and essentially a tanker would come in, drop the water, and then people would go out and measure the water in the cups.
The challenges with using the cup test method is that it's very timely. It involves a lot of people. Sometimes the water can completely miss the cup, so that means we have to do it over and over again, which costs more money and creates more time. And then also sometimes the water bounces out of the cup, so we don't get an accurate measure of the water. We are using cup tests to cross-validate this method with the infrared method. The benefit is we don't have to worry about the air tanker hitting the cups. We can just get it in the field of view of the camera and measure the drop footprint.
So with this information, we're going to create a library, so to speak, of different drop footprints and of course the concentration of water within those footprints for the various tanker types. And by recording other information like the weather, the altitude of the aircraft, the speed, we can start to work up little models of the factors that affect the size and distribution of water from air tankers. And over time we'll have a library where we can build some predictive tools based on those factors. So our approach to this data collection is innovative, and we are fortunate to work with folks like the Canadian Forest Service to provide the expertise and technology to be able to record this data. And of course our partnerships with FPInnovations and other agencies, Manitoba and Minnesota, to pull off these trials is one of the key contributors to our success.